On the left side of this slide, there are two pictures. One of a bicep muscle at rest with a myofibril, not a muscle fiber, also at rest. On the bottom, we have the biceps brachii muscle contracting, and we can see that the one myofibril is shortening. Recall from another mini lecture that Z lines are the boundaries of sarcomeres, which is the smallest subunit of a muscle that can still shorten in a contraction. Let's also highlight the Z lines over here on the contracted muscle. Compare the top with the bottom. The Z lines on the contraction of a sarcomere, they get closer together. Look at the H zone. The H zone seems to get a lot smaller. In fact, so do the I bands. They get smaller too. The only thing that gets bigger are the A bands or the dark bands, which are those areas of overlap. This is because as a contraction occurs, actin and myosin slide past each other. As they do this, the sarcomere shortens, but so do all of the sarcomeres on a myofibril. And then so do all the muscle fibers that contain those myofibrils. This starts a chain reaction. The muscle fibers shorten, pulling on the endomysium, which pulls on the paramysium, which then pulls on the epimysium, and then pulls on the tendon or aponeurosis attached to the bone itself. Just a reminder here that we are looking at skeletal muscle, which is defined by its attachment to a bone. Let's do some labeling here before we even get started, right? Always establish the anatomy first. The big blue thingies at the bottom of this slide are the thick filament made of a lot of myosin with its heads, hinge, and tail. The reddish spheres here are the actin subunits of the thin filament. The purple line that seems to twist around the actin subunits is that protein that is called tropomyosin. Take a really close look at the thin filaments on the bottom pictures. On the left, which is a relaxed muscle, tropomyosin seems to cover those active sites on the actin subunits. By covering them, the myosin heads can't connect to make a contraction. But on the picture on the right, representing a contracted muscle, tropomyosin seems to have twisted to reveal those actin active sites. In fact, you can even see this one myosin head here attaching to the active site and forming something that we call a cross bridge. Let's label that one. There is one more protein called troponin. This is the three-part structure that you can see more clearly in the top pictures. On the left picture, troponin is holding tropomyosin in place and covering the actin active sites. In the picture on the right, there is a green calcium cation from the sarcoplasmic reticulum that is attached to the troponin, and the tropomyosin is not covering those active sites. Again, allowing myosin head to form a cross bridge. All right, so now let's put it into motion a little bit. If a muscle fiber becomes flooded with calcium from the sarcoplasmic reticulum, all of these calcium cations will attach to these troponins. Calcium is like a key, and troponin is like the lock. So putting the key into the lock will open the door, or putting the key into the lock will move tropomyosin to reveal those active sites. So not only do these two pictures here illustrate what a cross bridge is, the attachment of a myosin head to an actin active site, these pictures also show us a comparison of a relaxed muscle on the left and a contracted muscle on the right. Okay, so cross bridges are analogous with contraction. Yes, yes, yes. In fact, a million little cross bridges are forming and breaking and reforming when you contract a muscle. They do this in a cycle that people can sometimes call the cross bridge cycle, as if you needed me to explain that one, right? The picture here shows that cycle, breaking it down into a couple of steps. This picture starts at 12 o'clock. Not the time, but the location. So this is the start. This picture at the top, this is the first picture that you should look at, and then kind of look at the structures going around from start to finish. Let me give you another. There we go. Before I explain these, you should do something. At this point in the mini lectures, we've defined every anatomical structure that you see on this picture. We just haven't put it all together. I challenge you to do that before listening to the rest of this slide. Go to each picture and just describe what you see. You don't have to interpret the picture, just describe it. For example, let's do the first picture together. I see that the myosin head of the thick filament is in a resting position. The myosin head is not attached to the actin active site on the thin filament. Tropomyosin is covering those active sites. Troponin does not have calcium attached. Okay, so now you go and do the rest of the pictures. I'm kidding. So if you do the rest of the pictures, did you use the word cross bridge for picture 2? If not, go back and do that. Make a statement about how this cross bridge has formed. Picture 3 has an added arrow to indicate movement. This is what is referred to as the power stroke. And the power stroke is the sliding of the actin filament past the myosin filament. This is when the two filaments, they slide past each other with a ratcheting motion. This is a theory, not a fact. Sliding filaments is a theory with a lot of support. Although no one has ever seen sliding filaments or a cross bridge directly with all of the fancy microscopes we have, like electron microscopes, we have seen shadows that tell us that this theory of sliding filaments is probably pretty close to the truth. Okay, at this point, I would like to point out that a cross bridge and the power stroke have all happened without the use of ATP. Up until this point, we have used no energy. You don't need any energy to make a contraction. You don't even need any energy or ATP to make the power stroke happen, despite its misleading name. So these first 3 pictures here illustrate how the movement of a contraction is created. Picture 1, picture 2, picture 3. They all tell you how the movement of a contraction is created, how the shortening of the sarcomere happens, making that disarticulated arm over there on the left side of the screen contract. And again, I want you to note that to make a contraction, there is no energy required. So while making a cross bridge and allowing the filaments to slide past each other, that requires no ATP. But resetting the filaments, breaking that cross bridge, and resetting them to be able to have another contraction, that needs ATP to happen. More specifically, ATP is needed to detach the cross bridge and reset the filaments to have a second, third, fourth cross bridge. That is exactly what you see in these last two pictures here, picture number 4 and picture number 5, if you're labeling them with numbers. In picture 5, the cross bridge is detached and ATP is present. If we cycle back again to our beginning picture, not only is the cross bridge detached, but the myosin head is also, it's cocked back into its original position. And ATP is not present on the beginning picture of this cycle. In fact, ATP is only present in these two right here that have to do with resetting the contraction. ADP is present because we have used the ATP molecule to detach the cross bridge and cock the myosin head back into its original position. This is what allows the cycle to start again. Writer's cramp is the result of not enough ATP in the muscles of your hand. It's because these muscles are designed for sprinting through a quick quiz, not marathon essay writing. These muscles naturally fatigue quickly because unless you want to breathe heavily as you write, you're actually not bringing in enough oxygen to allow these hand muscles to detach their cross bridges. The cramp, or the inability to move, comes from too many cross bridges attached and no ATP to reset the cycle. It's like they all did their power stroke, but then they couldn't finish the cycle. Rigor mortis occurs in the same way as writer's cramp. Rigor mortis is, it's basically the last contraction you will ever have. It is the last cross bridge that you will ever make. And you don't need ATP to make a cross bridge. So about 24 hours after death, your body stiffens up as your muscles make as many cross bridges as they can. Hours later, the actin and myosin proteins will actually start to break down and degrade. And this is what releases the body from the stiffness of rigor mortis. We're not detaching those cross bridges because in death there is no ATP. But as your tissues start to catabolize, then the cross bridges break and the filaments break down.